Good morning, students. Today we are going to discuss about battens. Battens are horizontal members which are used to connect the main members in a built-up column. Okay, so unlike what we have studied in the previous class, that is lacings. Lacings are inclined members which are used to connect the main members in a column. Okay, so here you can see that the main members in a built-up column will be connected in horizontal will be connected by horizontal members, and these members are known as battens. Okay, and these battened columns are mainly used for axially loaded compression members. Okay, that is when the load is acting concentrically. And flat bars or plates are most commonly used, but angles, channels, or I sections may also be used as batten members. Okay, and also it connects components of built-up columns in two parallel planes. It is used to connect the components of built-up columns. If this is the top view of a built-up column and it is connected on either side of the I sections, such in such a way it is connected in two parallel planes of the built-up columns. Okay, as you can see in this figure, this is a cross section and top view of a built-up column which is made by two I sections, and it is connected on either side using battens. Okay, there are some important terms in the batten column. So you can see the first one is overall depth of the batten plates, which is represented by D. The next term is effective depth. Effective depth is the, if this is the batten plate and it is connected with bolts to the main member, the effective depth is the distance between the outermost bolts in the vertical direction. Okay, or the longitudinal direction. Longitudinal direction means in the lengthwise direction of the column. Okay, so that is the effective depth of battens. Then another term is spacing of the battens. Spacing of the battens is represented by C. It is the distance between the centers of two consecutive battens longitudinally. Okay, and you can see small letter A, and it represents the distance between, that is the inner distance between the innermost bolts. Distance between the innermost bolts. And there is another term S. S represents the minimum transverse distance between the centroid of bolts, centroid of bolt groups on either side. So you can see there is a group of bolts in the first member and another group in the second member. So S is the distance between the centroid of the bolt groups. Okay. So we need to design the spacing of battens, overall depth of the batten, thickness of batten, and the attachment to the main plate. Okay, and the general requirements of the batten members are given in clause 7.7.1. Okay, it is about battens, it is shown in clause 7.7. You can check in your code IS 800. Clause 7.7 deals with the batten column. In page number 50 you can see, and all the important specifications and general requirements are given in clause 7.7. Okay, so the design specifications is more important for doing our problems. Okay, in general requirements, the main thing that is discussed is about the effective slenderness ratio. Effective slenderness ratio of a battened column is equal to 1.1 times slenderness ratio, actual slenderness ratio. That is, we are discussing about columns, and it will have a slenderness ratio. Slenderness ratio, lambda is equal to effective length by least radius of gyration. And if it is connected by battens, then we have to find the effective slenderness ratio. For a battened column, we have to find effective slenderness ratio, and it is equal to 1.1 times actual slenderness ratio. Okay, whereas for a laced column, the effective slenderness ratio is equal to 1.05 times actual slenderness ratio. Okay, uh, then we will come to design of battens. Okay, important design specifications. The first one is the forces in battens. Just like in lacings, the batten shall be designed to carry the the batten should be designed to carry the bending moment and shear force which is acting longitudinally, and it is arising due to the transverse shear acting on the battens. As we know, due to the axial load, there will be transverse shear acting on the batten plates, and from this transverse shear, the battens will have longitudinal bending moment and longitudinal shear force, and our battens should be designed to resist this longitudinal shear force and longitudinal bending moment which is arising from the transverse shear. Okay, so the transverse shear is equal to 2.5 percentage of the axial load. Just like in lacings, we have to find the transverse shear force, and from this transverse shear force there will be longitudinal shear and moment, and the longitudinal shear force is given by V1 is equal to V into C by NS. Okay, V into C by N into S, and it is given in IS code. Actually, all these are given in sentences, so it is difficult to find them. So you can see the longitudinal longitudinal shear force V, here it is given as VB. It is equal to VT into C by NS. VT means transverse shear into C by NS. Okay, and where C is the spacing of battens and N is the number of parallel planes. So in a battened column, N will be equal to 2. On either side of the main members, there will be one pair of uh, batten plates. So N will be equal to 2, number of parallel planes of battens. Like if it is an I section, you can say that there will be N equal to 2. Whereas if it is something like this, if we, for angle sections here, N will be equal to 4. Number of parallel planes will be equal to 4. Okay, that is a complex question. So normally we will have problems in N equal to 2, but just understand what is N. Okay, and S is the minimum transverse distance between the centroid of rivet and bolt group. Okay, suppose this is the centroid of the rivet and bolt group, and this is S. Okay, and likewise we can find um, longitudinal bending moment also, longitude which is given by Vc into 2n, where V is the transverse shear, C is the spacing of battens, N is the number of planes. Okay, and after finding out the shear force and bending moment, we will find out the we have to check for the longitudinal shear stress and longitudinal bending stress. Okay, the longitudinal bending stress which is uh, due to the longitudinal shear force it is given by tau is equal to V1 by d into T. Okay, shear force divided by cross sectional area d into T will get longitudinal shear stress, and it should not be greater than the permissible average shear stress. Permissible average shear stress is given by Fy by 1.1 root 3, and this should not exceed. Okay, and next one is check for bending stress. Sigma B is equal to M by Z. Bending stress sigma B is equal to bending moment by section modulus. Okay, this is coming from simple bending equation. M by I is equal to sigma by Y. Okay, from this sigma is equal to M by I into Y. We can write it like this. I by Y is section modulus. Okay, therefore sigma is equal to M by Z. Okay, so bending stress, you can find M by Z is equal to d square into T by 6 for this rectangular section. Now this equation we have to find it yourself. It won't be given in the steel table, so you can get bending stress and check it with the permissible bending stress in tension and compression, which is equal to Fy by 1.1. After checking for bending stress and uh, shear stress, longitudinal shear stress, then we will find slenderness ratio. Effective slenderness ratio of the battened column is equal to 1.1 times actual slenderness ratio. And then thickness of battens. There is a minimum requirement for the thickness of batten, and it is given in clause 7.7.2.3 in size. Under the subheading size, it is given, it is in a big paragraph, it is given here in the first portion of the paragraph. It is discussing about depth of the batten plates, and the last portion it is discussing about thickness. So here we want thickness, so it is given like the thickness of the batten shall not be less than 1/50th of the distance between the innermost connecting lines. 1/50th of the distance between the innermost connecting lines. Okay, that is we have already told before. A means distance between the innermost bolts, distance between the innermost connecting bolts. So that is A, and thickness should not be less than A by 50. That is, thickness of the plate should be always more than A by 50. And next is to find the depth of the battens. In that same clause you can find specification for depth also. So the depth is given for different cases. It is discussing about effective depth of the column, and it is given as for n battens and intermediate separately. It is given n battens means the battens which are given on the top and bottom of the built-up column. This is known as n battens, and all the battens coming in between is known as intermediate battens. Okay, so for n battens it is given that the effective depth should be greater than AI, where AI is the distance between the centroid of main members. Distance between the centroid of main members. So here it is different. In the previous, for depth we told it is the distance between the innermost connecting lines, whereas for thickness we discussed about distance between innermost connecting lines, whereas for depth it is the distance between centroid of main members. Okay, So D should be greater than centroid of distance between the centroid of main members, that is AI. And for intermediate battens, D should be greater than 0.75 times, it is AI same only, distance between 0.75 times distance between the centroid of main members. So you can see it in the clause itself. So in the clause, in the front starting portion, it is given for end battens, the effective depth longitudinally should not be less than perpendicular distance between the centroid of the main members. Okay, D should not be less than distance between the centroid of main members. And for intermediate battens, it shall have an effective depth of not less than 3/4, that is 0.75 times of the same distance. Okay, so it is given in sentence, so you can study in equation itself. I have to change here, it is AI, there is a slight correction in the notes. And there is one more check which have to be done. D should be greater than 2 times B, where B is the flange width of the member, or it is defined in code like this: width of the member in plane of the battens. Okay, that is in the plane of battens, what is the width of the member? So here it will be the width of the flange. Okay, width of the flange itself. And now after that we have to find the spacing, check for spacing. It is similar to our lacings. C by minimum radius of gyration of the component member, that is the value of R value, minimum R value, which we obtain directly from the steel table, and it is to be checked with, it should be less than or equal to 50 or less than or equal to 0.7 times lambda whole. Lambda whole means we have to find effective slenderness ratio of the whole column by considering R Z. If we are considering the whole column, means we have to take R minimum as R Z itself. Even in the steel table, if Ry is less than Rz also, we have to take Rz value itself, because in a built-up column Rz will be always less than Ry. Okay. Okay, so now we will be going for a problem. The question is, design a battened column with 2 channels back to back of length 10 meter to carry an axial factored load of 1400 kilonewton. The column may be assumed to have restrained in position but not in direction at both the ends. Okay, that is the question. So we'll come to the answer. First we will see how the column is. The end conditions are given: restrained in position but not in direction, that is the both ends are hinged or pinned. So it will be effective length will be equal to length itself. Okay, and here we are assuming the FCD value for channel section. We are assuming FCD is equal to 135 Newton per mm square, and from the assumed FCD value, and we know that compressive strength P is equal to effective area into FCD. Assuming P as the factored load given, we can find area required is equal to that factored load divided by 135. Okay, factored load divided by FCD, assumed FCD value. Factored load is in kilonewton, so we have to convert it into Newton raised to 10 cube. So we'll get the area required, 10,370 millimeter square. Okay, so this is a built up column. It was told that we have to take two channel sections. So try two channel sections such that the total area will be more than 10,370. Okay, so our assumed section is ISMC 350 at a unit weight of 42.1 kilogram per meter. So in the steel table, we have to find that first. After seeing the effective area required, check for all the sections whose area is almost half of that, so that if you take two sections, in total it will be more than 10,370. Okay, the section we choose is ISMC 350. This section, it is given in page number 6, and just see all the important properties. Okay, so area provided is equal to 2 times 5366. The area we found is, it will be 53.66 centimeter square. So here we have, we want the unit in millimeter square, so area will be 5366 millimeter square. So into 2 is 10,732 millimeter square. It is greater than the area required. Okay, and first we have to check for RZZ. Okay, because we are doing for a built up column. So value of RZZ is 136.6. Actually in table you can see that RY value is 2.83 centimeter and RZZ will be 13.6 centimeter. Actually the lesser value is RY, but we are choosing RZ value or RX value, 113.66 or 13.66 centimeter or 136.6 millimeter for this built up column. So we choose that and find the slenderness ratio of the whole section, KL by R minimum. So KL is 10 point, we know that it is 10 meter length and K is 1. So 10 into 10 cube by RZ is 136.6. So we got lambda whole as 73.206, and for a battened column we have to take it as effective slenderness ratio equal to 1.1 into KL by R. Okay, so we got 80.52. So in the lacings also we had to do this step, but actually in that note it was not written. So just check that and correct it accordingly. So using this effective slenderness ratio and for a built up column and channel section, we have buckling class SC, and check for buckling class, check for the FCD value from table 9C. So after interpolation we will get FCD value equal to 135.22. We have to do it and check the answer, and it is 135.22 Newton per mm square. And using this FCD value and the correct area provided, find the load carrying capacity of our column, and it is found to be 1451.2 kilonewton, and it is more than 1400 kilonewton. Okay, so after this we have to give spacing for the channel sections. So the channels are placed back to back, and to find the spacing between the two channels, clear spacing between the two channels, we have to find the modulus, this is moment of inertia about both the axes, because this is a built up column. We have two sections, so in both directions x direction and y direction we are finding moment of inertia. In x direction we have to find 2 times of ixx plus actually uh, here plus area into d square you have, but d is the distance from centroid centroid of the whole section to the neutral axis of the one section. So here in the x direction or z direction horizontal plane both are same, so uh, we can find ix equal to 2 times the value itself, ix itself, because d equal to 0. Whereas for Iyy moment of inertia about y axis 2 times Iy plus a into x bar square is the distance from neutral axis of the whole section to the neutral axis of the individual section. So here it is found that x bar is d by 2 plus 24.4, but d by 2 is the d is the actual distance clear spacing, so half of that plus 24.4 is the centroidal distance in the y axis, about the y axis for this channel section. The 24.4 we will get from the steel table, that is for ISMC 350. Cy by center of gravity about y axis it is found as 24.4, you can get it, so it is 24.4 mm. Okay, so that is x bar. X bar is d by 2 plus 24.4 whole square. So after doing that we will get the answer, and we have to equate for finding out d, we have to equate ixx and iyy. By equating we will get d is equal to some value. Here we go, d is equal to 218.4, and we are providing a value more than that, it is 220 millimeter. Okay, so the clear spacing is we found out as 220 millimeter by equating the moment of inertia about both the axes. Okay, now we have to find out s. S value is the, what is the definition of s value? S means the minimum distance between the centroid of the bolt groups on either main members. Okay, minimum transverse distance between the centroid of bolt groups. So we are assuming that the distance of centroid of the bolt group as 60 mm from the end of the plate. So either side we add 60 mm with the clear spacing 220. So 220 plus 60 plus 60 equal to 340 mm is the S value. So using these values we will start designing our battens. So we are assuming the C, we have to find C value by finding that condition, by using that condition. So let C be the spacing of battens longitudinally. This is the value of C. This is representing C, longitudinal spacing between batten plates. So R minimum of the channel section is 28.3. Actual R minimum is 28.3 mm, and so we are checking C by R minimum of component member. C by 28.3 should be less than or equal to 50. That is the first condition. C by 28.3 less than or equal to 50. From that we can get C as equal to 1415 mm. So that is for the first condition, and we are checking for the second condition as C by 28.3 and less than or equal to 0.75 0.7 times slenderness ratio of the whole member. So we already found the slenderness ratio of whole member as 80.52. So similarly, just as we did just before, finding C value as 1595. C value should be less than or equal to 1595. So taking the lesser value, we got this 1415. So it should be less than 1415. So we took a value of C as 1200. Okay, just don't make a mistake here, that it should be less than, the spacing should be less than these values. Okay, so take 1200 mm. So next we have to find transverse shear force. V is equal to 2.5 times 2.5 percentage of axial load. Axial load is 1400 kilonewton, make it in newton, and we found transverse shear force equal to 35,000 newton. Okay, 35 kilonewton or 35 into 10 cube newton. So from this, find the longitudinal shear force. V1 is equal to V into C by NS. C we already found out 1200, N is 2, and S is 340. Okay, and find the value of longitudinal shear as 617.65, 61.7 kilonewton. Okay, and longitudinal moment as M is equal to V into C by 2N. Substituting, we will get, okay, this much values in Newton meter. Now we have to find the size of battens. After finding the size, only we will check the stresses. Okay, first one is effective depth. Effective depth for end battens and for intermediate battens. So we have the condition like end batten should be effective depth of the end batten should be greater than or equal to centroidal distance of main member, and it should be greater than or equal to 2 times width of flange. Okay, so AI is the centroidal distance between main members. So it is found out as, we know that clear spacing is 220 and centroidal distance of either channel sections is 24.4. So adding all these, we will get centroidal distance between members as 268.8 mm. That is centroidal distance, and our D should be greater than or equal to 268.8 mm, and it should be greater than or equal to 2 times flange width. From the steel table, you can get width of flange of the channel section as 100 mm. Okay, you can see width of flange here, the value is 100 mm. Okay, and by checking both of them, provide 270 mm. D should be greater than 268.8, so we took it as 270 mm for end battens. And assuming an edge distance of 35 mm, the overall depth will be equal to 270 plus 2 times edge distance on either side. Suppose this is the batten, we found out that effective depth is equal to 270. So on either side it will have end distance. It is assuming as 35 mm. So D plus 35 plus 35, we get the overall depth. It is 340 mm. And for intermediate battens, we have the condition D should be greater than or equal to 0.75 times AI. Just like the same, and see how much it is. Here it is not given. There is a correction in the note, so it was deleted. So find similar way, substituting the value of AI 268.8 here and see the value of D, and also check for D greater than or equal to 2 times width of flange, 2 times 100, so it is 200, and we are providing D is equal to 260 mm, which will be greater than the both this condition. Okay, so overall depth in this case, and this is for intermediate battens, and the overall depth is equal to 260 plus 2 into 35, and it is equal to 330 mm. So overall depth for both the cases is found out. Depth is found. Now thickness we have the condition thickness should be greater than 1/50th of A. What is A? A means distance between the centroid of bolt groups on either main members. Okay, so we already found it before, so that is 340. We are assuming the bolt group as centroid of bolt group as 60 centimeter from 60 mm in either side. So clear distance D is equal to 220 plus central distance 60 plus 60. Okay, central distance of bolt groups. So we already found that before, that value is 340, and it is found that T should be greater than 6.8 mm. So provide 8 mm thick plates. So we got width also we got, and thickness is 8 mm. Now we will check for stresses. Okay, now we are doing it for intermediate battens. So the shear, first we are checking for shear stress. Shear stress equal to V1 by D into T. D is 330, capital D is 330, and thickness is 8 mm. Substituting we get 23.39 Newton per mm square, and it should be less than permissible stress, that is Fy by 1.1 root 3. It was 131.21, and our shear stress is longitudinal shear stress is less than that value, so it is okay. And now check for bending stress. Sigma B is equal to M by Z, and substituting the value of Z, M by D square T by 6, it is the value of sigma B. So rearranging it, we will get 6m by D square T. Okay, substituting the value of M in Newton meter and D as 330 mm square and T as 8 mm, we will get the bending stress as 72.3 Newton per mm square, and check it if it is less than the permissible bending stress Fy by 1.1. Yes, it is. Take Fy as 250 MPa, and we got it as 227.27. It is less, so here it is okay. So we are checking this one, what the intermediate batten, because it is having thickness, it is having depth less than the end plate, so that is more critical. So if the intermediate batten satisfies, then end batten will also satisfy, because end battens are more deep, having depth more than intermediate batten. So that point is given in the last sentence, and battens will satisfy these requirements since it is a deeper member. Okay, so that is the design of battens.